400 level student of the Department of Statistics, University of Illinois. So I'm going to be taking us through Introduction to Survivor Analysis. So these are the contents of what we are going to be doing today, the Introduction to Survivor Analysis. Our contents are the Introduction to Survivor Analysis, the Kaplan-Meier survivor curves, the log rank text, and the cost proportional hazard model. So before we go into the practical aspect, we have to give you the introduction, that is the theoretical introduction, so that you will understand the practical aspect. So what is survivor analysis? Survivor analysis is the collection of statistical procedure for data analysis for which the outcome of a variable of interest is time to an event. What this definition is just telling us is that survivor analysis is just the time to an event occurring. And when we say time, we mean in years. Your time can be years, it can be months, it can be weeks, or even days from the beginning of follow-up of an individual until an event occurs. Alternatively, time can refer to the age of an individual when the particular event occurs. So if we are saying events, if we are talking about events, event is what? Like deaths. In the survival analysis, we usually talk about deaths, disease incidents, relapse for emission, recovery time, like time to return to work, from marriage to first birth, from first birth to second birth, from secondary school to admission. So that is just what survival analysis is telling us about. Survival analysis deals with time to a particular event occurring. In survival analysis, we usually refer to the time variable as the survival time. So the time variable we are measuring is the survival time because it gives the time that an individual has survived over some follow-up period. So we also typically refer to event as failure. Usually in survival analysis, we usually deals with the failure. Like if the time to the arrest of a criminal, that's a parole, the time to the arrest of the criminal. So it usually deals with the failure of a particular event. So because the event of feature is usually death, disease incident, or some other negative individual experience. So in survival analysis, we talk about the negative effects mostly. So let's move to the next slide. So survival data analysis is considered to be merely the application of two conventional statistical methods of a special type of problem. It might be parametric and non-parametric. It's parametric in the sense that if the distribution of the data is known to be normal, we call it a parametric distribution. While if it is not normal, it is called a non-parametric distribution. In statistics, we all know what a parametric distribution is and a non-parametric distribution. Parametric distribution is a distribution that the examples of a parametric distribution, we have the normal, the binomial, the exponential, and the likes. And the non-parametric distribution, that's where we have the sign test, the rank test, and the weight concept test for statistics. In survival analysis, there are some terms you should know. Example of those terms are sensory. So here I defined what sensory is. Sensory is a condition in which the value of a measurement or an observation is partially known. When you don't have a full information about the data you are measuring, that's what we call sensory. There are generally three reasons why sensory may occur. In survival analysis, there are generally three reasons why sensory may occur. One, if a person does not experience the event before the study ends. For example, now we are to study the time to which 10 experimental rabbits dies after the administering a particular drug to them. So if we can give a time frame for that study, like let's say the time frame for that particular study is, we are giving that study is, let me say a month. So after administering this drug, at the end of this study, if out of 10, we only have 5 rats dying, that means the remaining ones that did not die are censored. So that's one of the reasons why sensory occurs. So because we don't know the time at which that particular rat dies. Are you following? So those rats that did not die are what censored. Another one is a person is lost to follow up during the study. Let me use that in example of rats. The 10 rats for the study period of a month. From those 10 rats, probably one or two of the rats escaped the cage. So those rats that are lost to follow up are also what? Censored. So that's the second condition. And the third condition is what? A person withdraws from the study because of death. That is, if death is not the event of interest or some other reason. For example, that same 10 rats, if our interest, if our interest is not the death of the rat, maybe till the rat develop a particular symptom, and along the line the rat dies within that study, so it is also called censored. There are basically three types of sensory. We have the right sensory. So I've explained sensory. So basically we have three different types of sensory. So we have the right sensory, the left sensory, and the interval sensory. When we say the right sensory, I've given an example of those 10 rats. So the right sensory occurs when a subject leaves the study before the event of interest occurs, or the study ends before the event has occurred. Just like the example I gave on the 10 rats. If those 10 rats, one of the rats escaped before the end of the study, or it dies before the end of the study. So that is what we call the right sensory. For the left sensory occurs when it is known that the event of interest occurred prior to a certain time t, but the exact time of the occurrence is not known. For example, let me use human being for example. At the age of 20, at age 20, you went for a particular HIV test. So that HIV test, you tested negative at age 20. So at age 30, you now went to test for HIV. You now went to test for HIV and you discovered that you are HIV positive. So that is what we call the no, the one I just explained is the interval sensory. The event occurs within an interval. This one I'm explaining now is the interval sensory. At age 20, you tested negative for HIV, but at age 30, you tested positive for HIV. So that is interval sensory. Interval sensory occurs when an event of interest is known to have occurred between time A and time B. So that is interval sensory. But left sensory, at age 20, you went to test for HIV and you discovered that you are HIV positive, but you don't know the time at which you contracted that particular disease. So that was what we call the left sensory.
Come again on the left sensory.
Left sensory, you went to test for HIV at a particular age, 20, and it was discovered that the person has HIV at age 20. But the time at which that person had contracted the disease was not known. So that is left sensory. Maybe it was when the person was 5 years, 10 years, but it was not known. That's what we call the left sensory. But the interval sensory, you tested at age 20, you were negative, but at age 30, it became positive. So the time where the person contracted that particular disease between the age of 20, where the person tested last, and the age of 30, when the person tested that he or she has that particular disease. Left sensory, let me come back again. Left sensory, the time at which the event of interest occurred was not known. Look at it. Occurred when it is known that the event of interest occurred prior to a certain time t, but the exact time of the occurrence is not known. Prior to a certain time t, prior to the the age of 20, your event has occurred already before that age 20, but the time at which it occurred, you did not know. So another thing to note there is the survivorship function, which is denoted by ST. This gives the probability that a person survives longer than some specified time t. That is, S of t gives the probability that the random variable t exceeds a specific time t, where s of t is the number of patients surviving longer than t over total number of patients. This survivorship function is just telling us the time at which the person survived. It can also be calculated as one minus probability that the person will fail before time t. So that survivorship function can be calculated as 1 minus the probability that an individual fails before t. It's like S of t is 1 minus probability that an individual fails before a particular time t. For example, we are testing, let me use those the 10 rat as an example. The 10 rat as an example. The probability that the rat is going to fail before that 1 month period of testing is what? Like, let me say the probability that it's going to fail, 1 minus probability that that rat is going to fail, that is what we call the survivorship function. So while the hazard function h of t of survival times gives the conditional failure rate, this is defined as the probability of failure during a very small time interval, assuming that the individual has survived to the beginning of the interval or has the limit of the probability that the individual fails in a very short interval. This one is just talking about the failure in interval, given that the individual has survived to a particular time t. We move to the next on the content, which is the Kaplan-Meier curves. The Kaplan-Meier curve is a non-parametric approach. It uses the Kaplan-Meier estimates, also known as the product limit estimate, to estimate the survival probability from observed survival times. It makes use of the Kaplan-Meier curve, which is right continuous step function. The Kaplan-Meier survival curves is just like a step right. It is like a step to the right. So when we get, I'm going to, in the next slide, you're going to see an example of how a Kaplan-Meier curve looks like. It is also used to get the survivorship function, this x of t. You can also use your Kaplan-Meier curve to get the x of t, which is written below as the what? The product of what? T of I less than t into bracket 1 minus di over ni, where s of t is the survivorship function, di is the number of deaths at the time I, and ni is the number of patients at risk at that time I. So when we do this thing, you are going to get, when we do the analysis, you are going to get it better when we do the analysis. So this is an example of how the Kaplan-Meier curves looks like. It is like steppy to the right. If you look at the curve to the left, the first curve to the left, it contains two covariates, gene A and gene B, which is like it's categorical in nature. You are testing. This is categorical in nature, and this is just a continuous function. Log rank test. The next on the in our content is the log rank test. The log rank test is just like the chi-square test, the large chi-square test. It compares the difference between two groups. It compares the difference between two groups. That is, the hypothesis is stated as the null hypothesis that the survival times of groups are the same, and the alternative hypothesis stated as the survival time of the groups are not the same. What this log rank test is what? For example, you are testing the survival rate of breast cancer patients, because that's the data we are going to be using for our analysis. You are testing the survival rate of breast cancer patients, and you know there are so many factors that determines the survival of breast cancer patients, like the stage of the cancer. You know, we have different stages of cancer. We have the stage 1, stage 2, stage 3. That's one particular covariate. Another one is what? The surgery type of the patient. Another one is what? The HER status. So in that particular cancer stage, you know, we have stage 1, stage 2, stage 3. So the log rank will test if the survival times of these stages are the same. Survival time of stage 1 is the same with survival time of stage 2, or survival time of stage 2 is the same as survival time of the stage 3. So that is what the log rank tests. So, and the formula is given below as what? It's just almost the formula for chi-square distribution. It's distributed chi-square with g minus 1 degree of freedom. Let's move to the cost proportional hazard model. This is a semi-parametric method of regression model. If you look at the formula there, it is very similar to the regression model. Look, let me just read one. The cost proportional hazard model is a popular mathematical model used for analyzing survival data. The cost proportional model possesses the property that different individual has hazard functions that are proportional. The cost model is given below, which the h of t, this is the hazard function, is what? This h naught of t is the hazard, the baseline hazard function. H naught of t is the baseline hazard function. Why this exponential of the b1 x1, b2 x2, and to bp xp? These are just the coefficients of the various covariates. That means the patient you are studying, whether survival of patient or the time to marriage or time to admission, depends on what you are studying. So the H naught is the baseline hazard function. The estimated regression coefficient and the hazard ratio between the groups of covariates. The hazard ratio is used to interpret the cost proportional hazard model. The hazard ratio, it is used to interpret the cost proportional hazard model, and it is, sorry, the hazard ratio is used to interpret the cost proportional hazard model, and it is compared based on its closeness to 1. So when we do the practicals, we are going to get it fully. So I have given us the introduction to survival analysis. So we just have to move to the practical of survival analysis.